So today we're going to be looking at problem 1.4 from Fundamentals of Heat and Mass Transfer, 7th edition. And the problem is, the concrete slab of a basement is 11 meters long, 8 meters wide, and zero point 0.2 meters thick. During the winter, temperatures are nominally 17 degrees Celsius and 10 degrees Celsius at the top and bottom surfaces, respectively. If the concrete has a thermal conductivity of 1.4 watts per meter Kelvin, what is the rate of heat loss through the slab? If the basement is heated by a gas furnace operating at an efficiency of 0.9 or 90%, and natural gas is priced at 2 cents per megajoule, what is the daily cost of the heat loss? And I have underlined the things that we know as we read the problem. So let's start with our knowns. We have a length of 11 meters, a width of 8 meters, and a thickness, which I'll call T, of 0.2 meters. For our temperatures, we have the temperature at the top at 17 degrees Celsius and the temperature at the bottom at 10 degrees Celsius. Our concrete has a thermal conductivity of 1.4 watts per meter Kelvin. And for our furnace, our efficiency, eta F, is 0.9, and the cost of gas is going to be 2 cents per megajoule. So that is what we know. We need to find, it looks like, two things. So number one, the rate of heat loss through the slab. So the rate of heat loss, or Q, through the slab. And the ultimate goal is to find the daily cost of the heat loss. And we're just going to break it up into kind of two parts. You could arguably just write the daily cost of the heat loss. So let's start our schematic. And we're going to draw a concrete slab here, sort of. We'll make it three-dimensional. And we have our thickness T, our length L, and our width W. And quickly want to draw the right things here. Our concrete slab has a thermal conductivity K and a heat loss Q. We have a temperature on the top surface, T top, and a temperature on bottom, T, I'll call it T bot. And we also are going to draw our furnace as a little box here. And we'll put the efficiency of the furnace in there. We're going to have natural gas coming in. And that has a cost of, that has a cost of 2 cents per megajoule. And we're going to have warm air coming out of the furnace. So now that we have our schematic, let's take a look at our assumptions. So what are our assumptions for this problem? Well, number one, we're going to have to assume steady state. We're also going to assume one-dimensional conduction. We don't have any information about convection or radiation, so we wouldn't be able to take it into account anyways. And the last thing is constant properties. So things like the thermal conductivity of the slab and the efficiency of the furnace, we're going to assume do not change. So that's our setup. Let's go ahead and move on to our analysis. So this is conduction, right, through a slab. So we're going to start with our conduction equation, which is Q, or heat loss, is Ka times dt dx. Let's break this down a little bit further into the variables we have. So K we have, our area is going to be the length times the width of the slab. dt, the temperature difference, is going to be the temperature on top, which is higher than the temperature on bottom. That will subtract from it. And the dx, which is perpendicular to the surface of the slab, right? This is the thickness that the heat is going through is going to be T, or thickness of the slab. So from here, we'll plug in our values. We have K of 1.4 watts per meter Kelvin, and we should look out, we want to have watts at the end. So because our Q is what we're looking for. Our length is 11 meters times 8 meters. I'm going to check real quick and make sure that's correct. Yeah, 11 meters and 8 meters. And our top temperature is 17 degrees Celsius minus 10 degrees Celsius. And we'll divide that by the thickness of 0.2 meters. And if we plug that into a calculator, we are going to get 4,312. Let's sanity check ourselves with our units. So we have a meters on bottom here and on top here. That cancels. A meters on top of our width and on bottom of our thickness. That cancels. And then because the only conversion between Kelvin and Celsius is adding 273 degrees or subtracting, depending on the way you look at it, we can actually cancel this Kelvin with the Celsiuses of the temperature. And that's because this temperature difference is going to be in Celsius. So we cancel the Kelvin with the Celsius. We're left with just watts. And so our answer is going to be 4,312 watts. Now we have to calculate the cost. So this is answer number 1. And our cost, which we'll call the daily cost, we'll call CD for daily, is going to be the heat loss rate, which is in watts, times the cost of natural gas, divided by the efficiency, which we have to take into account. And then if we just left it like this, we would actually be missing a unit. And we need our final answer to be in terms of days. So we are going to put a delta T term here for the amount of time. In this case, it's going to be just 1 day. So for Q, we know 4,312 watts, just about, is going to be our heat loss. Our cost is going to be 2 cents per megajoule. Our efficiency is 0.9. And we are going to go ahead and multiply by our time. What I'm thinking here is we might want to convert the megajoules into joules so that it works with our watts. So because this is 2 cents divided by megajoules, the megajoules is going to be on the bottom. And so I'm going to quickly multiply here by 1 over 10 to the 6th. And that's because there are 10 to the 6th joules in 1 megajoule. And because this megajoule will go down here, it'll cancel with that megajoule on top. We'll be left with a joule on bottom, which is what we want. Finally, for our time, we are going to turn this into seconds so that we can work with our watts unit. We have that joules per second that needs to cancel out. So we're going to have 24 hours times, and there are 60 seconds in 1 hour. Excuse me, that's not correct. There are 3,600 seconds in 1 hour. And that should be everything. Once again, let's sanity check our units. So the megajoules here is going to go on bottom, and it will cross out with the megajoules here on top. We have hours that will cancel, and we have seconds over joules. So we have seconds over joules, and seconds over joules is the opposite of joules over seconds, which is equal to a watt, meaning that our watt is going to cancel with our seconds and our joules, and we're going to be left with only dollars, which is exactly what we want. So if we plug this into the calculator, we are going to get a daily cost of $8.28 per day, which is kind of expensive if you think about it. Inflation, man. Lastly, our comments section. Not much to talk about here. You could add that this cost could be reduced by adding, I'm going to say a layer, but you could add multiple layer of insulation. And this would reduce the heat loss through the slab, which would reduce the cost per day. Heat loss through the slab, and therefore, well, I already said the cost could be reduced, so I guess I don't really need that. And that's our problem.